Hello everyone, welcome back to A to Z online study. In the last video, we learned about the basic staircase design and what are the checks we want to include in the staircase design. In this video, we will discuss about an example about the internal staircase in our buildings. Now you can see in the ground floor plan in two-story buildings. This internal staircase is inside the building, usually protected by walls, so it's safer from the rain and weather. In this plan, the staircase is placed near the middle left area, close to the car park. You can see in this image, and it concreted, and also this connected to the ground floor to the upper floor. Uh, in this image, this is the internal staircase area close to the car park and the washroom, and also this is the external staircase area. This is located near to the building wall. So, and also you can see the cross section view of this building staircase, internal staircase. We want to design first this part. After that, this part and this part are same, both are equal diagrams. So we want to design first this part. So all the staircase, internal staircase are same like that. Initially, for the internal staircase design, you show that image, the staircase plane, the staircase 3 meter in plane, and also the difference between the ground floor slab to the ground floor foundation level 3 meter. So different of the two levels is 1.5 meter. So this staircase like this. So this difference is 1.5 meter, and also this difference is 1.5 meter. So difference between the two levels is 1.5 meter. And also the characteristic compressive strength of the concrete is 20 megapascal. I assume this value. You can assume 25 megapascal or 30 megapascal. And also the steel reinforcement strength is 460 megapascal. I assume this value. These are the usual standard values for the steel and concrete. The next one is density of the reinforced concrete according to the Eurocode. You can see in the Eurocode the reinforcement concrete density is 25 kilonewton meter cube. And also I assume these values for the staircase design. The first one is top finishes on threads only. I explained in the previous video what is the thread, what is the rise, what is the going, what is the W, waste, all the terms are I explained in the previous video. The top finishes on the thread only, I assume this 0.5 kilonewton per meter square. And also soffit plaster means in the waste there is a simple plaster of the cement plaster, so that soffit plaster weight is 0.25 kilonewton per meter square. We want to first for the design we want to choose a staircase, number of staircase in that position. For that I choose 18 staircase in one level. So one level is 9 staircase. So the rise is the vertical distance between the level difference. So rise is equal to 1500 is the elevation difference from one staircase. this is the 1.5 meter. So the rise length is 167 millimeter. The next one, going is the horizontal distance between the one staircase. So going is equal to 2025 means the in the ground floor plan you can see these dimensions, the horizontal distance of the staircase, the beam length, then we want to divide it by 9 the staircase, so we can find the going uh, length to 225 millimeter. Afterward we want to check first the geometric check. For that check, the 2r plus g is equal to uh, 2r plus g value. 2 into r value is 167 plus g value is 225. So we can find 559 millimeter. So approximately this is 600 millimeter. So 2r plus g is approximately equal to, it should be 600 millimeter. This is the geometric check. And also, when if you want to find the noising of that staircase, in the previous video I told you that T is equal to tread is equal to noise plus going. We know the going length 225 millimeter. We know the tread length. Usually noise is, we don't know the tread length, so we want to find the tread length. The noise we took 25 millimeter, so tread length is 250 millimeter. After that we want to find the uh, effective depth. Effective depth means uh, to find the effective depth we want to assume the span over depth ratio. If you know the span over depth ratio for the staircase, these are the values uh, in the Euro code 991. The loading part, you can see the span over effective depth ratio. That ratio is 30. We know the span length 3,303 meters, so 3,000 millimeter. Span over effective depth ratio means span over depth. Depth is equal to 30. So 30 into span over 30 is to a depth. So depth means the waist thickness. In the staircase, the slab thickness, in the bottom part of the staircase there is a slab, so that thickness 100 millimeter. If we assume a cover, we want to assume the cover. In the cover design we want to assume an exposure condition. In this condition I assume the XE1 exposure condition, so the staircase cover is to 25 millimeter. And also I assume the bar diameter 12 millimeter. So H is equal to H means the slab thickness. H is the slab thickness. In the slab there is a cover part. There is a cover part. You can see this. This is the edge from the slab bottom to top part. This is the bar, T12 bar I assume. In the bar center to the slab top is the effective depth D part. So D plus bar diameter by 2 plus cover is the H, waist thickness. H means the waist thickness. So I found the waist thickness 131 millimeter. So 130 millimeter is the waist thickness. According to this waist thickness, the effective depth is 99 millimeter. I already found 100 millimeter is a effective depth. So these are equal values. So our span over depth ratio is correct according to this. And also in the according to the fire resistance, to have a fire resistance, H should be greater than 120, A should be greater than 20 millimeter. After the after these checks, geometric checks, and also the cover bar diameter assumptions, after that we want to calculate the loading. For the loading part, we want to take a vector for the slope. Vector for the slope. Slope vector. That means the slope vector. In the slope vector, equation is this. According to this equation, we want to find the slope vector. And also according to this equation, we want to find the overlap vector. So overlap vector and the slope vectors are one dimensions to the loading calculation. The first one, dead load for the staircase. Dead loads means this is come from the concrete weight. We know the concrete density is 25 kilonewton per meter cube. So waste load is waste thickness is 130 millimeter, and the waste width is 0.8 meter, and also the weight the concrete density 25, and also 1.25 is the slope vector. We can find the waste dead load in kilonewton per meter, and also we can find the steps um, dead loading, using this half into width into thickness into uh, concrete density into 1.5. 1 means we want to multiply by overlap factor for the steps. We can find the value, and also we can find the dead load from the top finishes, and also we can find the dead load from the soffit plaster. So total dead load in the staircase is 5.77 kilonewton per meter. The next part, in the ultimate limit state condition, we want to find the dead load and also imposed load. For the imposed load condition, I assume 4 kilonewton per meter squared for the staircase, and after that I multiply by the width of the staircase, so we can find the loading from the imposed load. So ultimate limit state, the design load means 1.35 into dead load plus 1.5 into uh, uh, UL imposed load. This is the Euro code standard. According to the United UK standard, that ratio is different. So after that we can find the ULS condition design load. This is the design load. After that we want to design for the bending. So in the bending design, we want to find the bending moment. For that bending moment, we want to take a value according to the Euro code. We can find the moment table. This table is continuous. This staircase is situated in the continuous beam, so we can find the bending according to the table is FL over 10. I assume this value. The table you can see 0.6 FL, but in here I assume 0.1 FL. So we can find the moment 11.339. And also after that we want to find the K value. K value is M over BD squared over FCK. We can find the K value 0.072. That is smaller than 0.167. So this 0.167 is the singly reinforced section standard value. So this is the singly reinforced staircase. After finding the K values, we want to find the set value. Set value should be smaller than 0. Set value, we want to take the set value, smaller value of these two values. Using this equation, we want to find the set value, and also this equation, we want to find another set value. Compare those values and get the smaller value, we say the set is the 92.45. This A is mean the reinforcement area required for this staircase. For the reinforcement area required is the M value is 11 point into 10 to the power 6. 10 to the power 6 means kilonewton per into meter into we want to get this into Newton into millimeter, so we want to multiply by 10 to the power 6. You can get the AS required, the reinforcement area required for this singly reinforced 307 millimeter. I assume already the bar diameter is 20 millimeter, 12 millimeter. So the three bars in the 307.414 divided by the bar area, it gives 3 bars. So in the width direction, we want to give the main bars 3 bars in the uh, width direction in the staircase. So in the 3 bars, what is the area provided? Area provided is 339.29 millimeter. If you want to find the spacing of that staircase, we want to divide the width divided by the bar number, so we can find the spacing. So we can tell the bar diameter 12 millimeter, and the spacing of that bars in the main bars direction. This is the main bar. Spacing is 250. This is the T12 bar. T12 bar. So 3T12 bar and 250 millimeter spacing is the main bar in the staircase. So we decided the main bar dimensions in main bar numbers. After that check, we want to check the minimum reinforcement check. This is the minimum reinforcement check. You can see the step by step procedure. After that, maximum spacing check. How to decide the maximum spacing, and also we want to check for shear for this main reinforcement. So this is the step for the shear check. After that, we want to check for the deflection. This is for the deflection check. After that, we want to check for the uh, um, after that we can say shear reinforcement is not necessary. So shear reinforcement for the staircase, there no need to put the shear reinforcement. Only the beam, we want to beam and column, we want to provide the shear reinforcement. After that, we want to design the distribution steel. We finish the main bar design. After that, distribution steel. For that, I assume T8 the thickness of the uh, steel is 8 millimeter. So we provide the distribution bars 300 millimeter. So we decided the main bar in the distribution bar in the staircase. You can see in this image of the final output, final design of the staircase. This is the ground floor plan. This is a typical diagram for the all the internal staircase in our building. We can put the staircase like the all the staircase. You can see this is the main bar. These are the main bars. This blue color part is the main bar. Main bar. T12 at 250 millimeter spacing. We want to put the main bar. Main bar. And also this red color part is the these are the distribution bar. These are the distribution bar. That distribution bars T8 at 300 millimeter spacing. And also in this distribution bar, these are the main bars. These are the main bars. These are the main bars. This blue color part of all are main bars, and also these are the distribution bars. The red color part all are in the distribution directions we want to provide on, and also we want to provide the another bars in the corner direction, corner area. We want to provide another bar like this way. We want to provide another small bar to connect to bottom bars, corner bars also. These are the typical internal staircase reinforcement detail. So this is a simple example of an internal staircase usually using the house plan. In the next part, we can do more detailed design step by step with bending moment and steel calculation. If you like this video, please like and share and subscribe to A to Z Online Study. Thanks for watching. See you in the next video.